So we are going to be continuing follow up with lesson 6.1, which was finding the area under the curve using some geometric methods. So we're going to be finding areas under the curve today using what's called a Riemann sum. So I'm going to share my screen and start the presentation. And my name is Mary Bird. I teach at Sandpoint High School in Sandpoint, Idaho, and we're going to be approximating areas using Riemann sums today. What will we learn? We'll learn how to approximate the area under a curve graphically, numerically, and analytically. We're going to be using what's known as a left approximation or an LRAM, as you see on your handout, a right approximation or an RRAM, and a midpoint approximation, which is known as an MRAM. And then we'll also do trapezoidal approximations. So if you're wondering what these letters actually stand for, LRAM is left rectangle approximation method. RRAM is right rectangle approximation method. MRAM is the midpoint of a rectangle approximation method, and so forth. All right, so let's get started. What this looks like graphically, you have a continuous function bounded by some function f of x. That's what this curve is here. And we've partitioned this into some somewhat rectangular shapes, and I can finish off the top and make them look rectangular. We're starting to find the area under the curve starting at A, and we're going to B. And so that's what this looks like. And so what we do with this method graphically, let me grab a pen here, is I'm going to, if I look here, I have 1, 2, 3 subintervals here. That creates 4 rectangles. So I start here. This is A. This is actually, say x0 on the graph. And this would be x1, x2, x3. And then my B is located at x4. That's a lovely 3. All right, and this is my function f of x. So if I'm trying to find the area here under this curve, and if I just look at one of these rectangles, remember that the area of a rectangle is equal to length times width. So one of the first things you need to do when you're finding the area of these rectangles is to figure out this, and we're going to talk about this width here. The length is actually, I don't know, whichever way you want to look at, the length is the height and the width is this distance here. So what I would do is I would take, well, I'm going from A to B and I'm dividing it into however many rectangles. In this case, I would have, I'm going from A to B, so the width of each rectangle is going to be B minus A divided by 4, right? Because I have 1, 2, 3, 4 subintervals. In general, though, I would do my right endpoint minus my left endpoint, and I would divide it by n, where n represents the number of rectangles, or you will most often see it referred to as subintervals. I'll see if I can get my pen to work here. So it's the number of rectangles, or we call them subintervals. All right, so that's my width here is this, and we call this delta x, or the change in x, like how our x is increasing. What's the change from this x to this x? So that's our delta x, and that's our width. And then the height of the rectangle, or the length of the rectangle, is, well, what's the value? If I plug A into my function, the height of this rectangle right here would be f of A. The height of this next rectangle, if I drew it across here, well, I should actually make it more like that. The height of this one would be f of x1, and so forth. And so the height of these is f of, and I'll just put xi, because I is just whatever some interval is, and that's going to get us the area under this curve. So the height of the rectangle times the width of the rectangle, right? And these things in here are called our subintervals. All right, let's look at our next slide. All right, numerically, we may see a problem like this. It says g of x is a continuous function from 0 to 25, where g of x is the rate that Catherine travels from her home to school. G of x is represented in miles per minute and x is in minutes. Let's find the distance that Catherine travels. All right, we're going to find the distance, and it says here, let me grab my pen, that we are going to do this using a left Riemann sum. All right, so we need to know what our width is, and this is a little different when they give you a table. We don't have to look at the graph. We don't have to look at the b minus a divided by n. We can look at how many spaces there are between these. So if I look at this first distance between these first two x values, we have 2. So the width of that first rectangle is going to be 2. From 2 to 6 is 4. 6 to 8 is 2. 8 to 15 is 7. 15 to 20 is 5. And 20 to 25 is 5. All right, now we want to use a left Riemann sum. So if I think for a minute, if I did graph these, all right, let's just draw a little graph. It looks like they are increasing. All right, this first one, at 0, I'm at 10. At 2, I'm at 14, 20, so forth. And then it starts to back down. So if I look at my first rectangle here, we know the width from here to here is 2. We just talked about that. The height of this rectangle, right, if I'm using a left Riemann sum, the height is this left value, the value at 0. So this one is going to be 10. If I look at my next subinterval, okay, this time the width of this rectangle is 4, and the height would be this height, right, which I look would be 14. So my first rectangle, and we're going to have, let's see how many we'll have here. Well, 1, 2, 3, 4, 5, 6 rectangles. So remember that distance is equal to rate times time. So when we do this, her rate times her time, right? Time is in minutes. This is a rate in miles per minute. When I multiply those two things, distance equals rate times time, that goes way back to elementary school. If our units for rate are miles per minute and our time is minutes, when we do this Riemann sum, we will be left with just the number of miles. All right, so again, the distance is going to be our first width, which we said was 2, and that first height of that first rectangle is 10. So we have 2 times 10 plus our next width is 4, and our next height we said was 14, because remember we're using left, so we're starting with this left height. Next we have 2 times 20 plus 7 times 15 plus 5 times 30. And our last width is 5. And we're multiplying it times 20. All right, so if we work all those out, the total distance that Catherine travels should be, and you can check my work here, make sure I did it right, 471 miles. Okay, so maybe she was off at college or something because she's traveling from home to school. Maybe she was going to college, right? She goes to school pretty far away, right? And that is our left Riemann sum approximation. This is a pretty typical problem of what you'll see on the AP exam. All right, let's look at another one. Okay, this time we're finding it algebraically. And so we have to do some work here. It says use a left Riemann sum to find the area of a region bound by y equals e to the x equals 1, x equals 3, and the x-axis. And it's telling us to use 6 subintervals this time. All right. So this time, and if you like a graph, you can always draw a little sketch of your graph. You find that helpful. All right, y equals e to the x. I know e to the 0 is 1. So my graph is going up exponentially. It's bound here by x equals 1 and x equals 3. So I'm trying to find the area of this region right in here under the curve. All right, I need 6 subdivisions. All right, we're going from 1 to 3. So remember to find that change in x, to find that width of each rectangle. My delta x is b minus a divided by n, where n is the number of rectangles or the number of subdivisions. So in this case, our delta x is going to be 3 minus 1 divided by 6, right? Because we need 6 subdivisions. So simplifying that, 3 minus 1 is 2, 2 over 6. The width of each one of these is going to be 1/3. So from this 1, I count up 1/3 and draw another rectangle. Then I go up 1/3 and draw another rectangle, right? So we're going to have then that, and we're using again a left Riemann sum. So we're going to have that our first rectangle, I'm going to write here, I'm going to write area left, is going to be equal to, all right, our first one starts at 1 and goes to 1/3. All right. And if we notice here, all of these are going to be 1/3 wide. So I actually can just put a 1/3 out in front because every rectangle in this case has the same width. Right. Now, I'm using my left endpoint here, right, left endpoint to find the height of this first rectangle. So the height of the rectangle is the value that we get when we put 1 into this function. This is y equals e to the x. Right, so the height of the rectangle is the same as e to the first. So we have, in this case, e to the first for our first rectangle, plus, right, again, the width is already 1/3. So if I'm at 1 and I go up 1/3 from 1 to get to this next subinterval, 1 plus 1/3 would be 1 1/3 or 4/3. So the next height is going to be e to the 4/3. Okay, I keep going. 4/3 plus 1/3 to get to my next rectangle is going to be e to the 5/3. Plus, keep going, e to the 6/3, which is 2. How will I know when to stop? When I put in this last value here. When I put in e to the 3rd, that's the end, right? That's going to be my last one. And if I have a, well, I'll just go, we'll just keep going. So we have e to the 2nd plus e to the, so this was 5/3, 6/3. This one is now 7/3. And then we have plus e to the 8/3. All right. Now we were doing 6 subintervals, 1, 2, 3, 4, 5, 6. All right, I'm not going to put it into my, and that's what I was getting to. I'm not going to put into this one because remember, we were doing a left approximation. So the last rectangle I'm going to have is going to be bound on the left by this height of the rectangle, which is my e to the 8/3. E to the 9/3 or 3 is up here, and it's not my last rectangle, right? So when it's a left, you're kind of leaving off this right-hand number. If I'm doing a right-hand approximation, I'm going to be leaving off this far left number, right? And so if you want to, you can type those into your calculator and get your approximation for this. And I don't think I did this one. Well, let's go ahead and check. So I'm going to type that in, and just don't forget that you're going to be doing, divide your answer by 3. So I'm going to have e to the 1st plus e to the 4/3 plus e to the 5/3 plus e to the 2nd plus e to the 7/3 plus e to the 8/3. All right, and if I do that, just before I even get my divide by 3 here, this number is going to be 43. And when you're doing these, remember your final answer needs to be rounded to the nearest thousandth, because we need 3 decimal places. These are really hard to read here. All right, that's 43.8996767. So the area is about equal to, and those should be wavy. So I'm going to divide that answer by 3. because we're taking 1/3, and I get that the area under the curve is about 14.633. Notice on these, we kind of leave off the units unless it's one of those where it's a specific problem like that last problem where we're finding the total distance that Catherine ran. If it's one like this, you can just leave this answer as this numerical value. All right, sometimes you're going to encounter problems that are written. You could have a table, you could have a graph. So it says use the data in the table to approximate the distance a car travels using, and this time we're doing midpoints. All right. Midpoints are kind of tedious to calculate unless it's one like this where they give you a nice table and makes it easy. So we have the midpoint of 5 subintervals, and we're going from 0 to 50. So the width of these rectangles, first of all, is going to be 50 minus 0 divided by 5. So 50 divided by 5 is 10. So each subinterval is 10 units long, right? So my first one, I'm going from 0 to 10, then 10 to 20, 20 to 30, 30 to 40, and 40 to 50. Now, if they hadn't given me a table, I would have to take whatever my y values are, add them and divide by 2 to get those midpoints, right? It's kind of a pain to do this. I'd have to actually do this. But if I look, each one of these subintervals has a midpoint number and a value at that midpoint. So when I'm doing this, I'm going to be using these values here associated with the midpoints of each one of these intervals, which really makes it a lot easier. All right, and if you look, these are the midpoints, right? I was going from 40 to 50, so the midpoint is 45, and I'm going to be using that 60. All right, so the distance then is going to be equal to, and I'm going to put my 10 out in front because the width of each one of these rectangles is 10, so I don't have to write it next to every one. And I'm going to add my midpoint value, so I'm adding 12 plus 30 plus 70 plus 81 plus 60. All right, so I'm going to add all those together and multiply by 10. And this would be one that would be pretty likely to be on a non-calculator part. They assume you can add these together. So if you haven't already done so, I got 253 for this. And if I multiply by 10, the total distance traveled is 2,530 feet, right? Look at your units here and you can figure out this is feet per seconds, this is seconds. So when we multiply those times a fraction, we're going to get 2,530 feet, right? Notice they gave it to us in the table, but we didn't need it, or excuse me, in the graph. We didn't need it because we had the table. All right, the next problem, if you notice on your sheet, is related to this one. It says, use the data from example 4 to approximate the distance a car travels using a right Riemann sum with 5 intervals. All right, so I'm going to switch colors here just so we can distinguish between these two problems. So if you're following along on your handout, I could go to my slide and see if it's, yeah, we've got it there. So we're doing a right Riemann sum, and this time we went subintervals of equal length from 0 to 50. So again, the width is still the same. Oops, go back, I lost my pen here. All right, we still have that the width is 50 minus 0 divided by our 5 subintervals, means the width of each one of the rectangles is 10. But this time we want a right Riemann sum of 5 subintervals. So our width then is still 10 for these, but now we're doing a right Riemann sum, okay? So I'm going to be using, for this first one, I'm going to be using a height of 72, right? Because that's the right end of that last subinterval. The subinterval before that, I'm going to be using 75, 78, 55, and this one was 20. All right, so it's 20, right? Because if I look at my first interval goes from 0 to 10. The far right edge of that one is 20, right? I evaluate this number at v of t, which is 20. and 55 and so forth. So you're using the right endpoints here of each subinterval. Okay, notice if it's a left subinterval, I'd be using 0 and so forth. Okay, but we're using the right. So I am going to find the distance this time. I still have my 10, the width of each rectangle is 10, but now I'm going to be adding 20 plus 55 plus 78 plus 75. Oops. Did I give my, no, that's right, 75, 78, 75, and our last one is 72. Yeah. All right, so this time, adding all those together and multiplying by 10, you should get this time that the distance is about 3,000 feet. Okay, so we don't know exactly what the distance is, but this one is quite a bit off from our midpoint. What was our midpoint? 2350 or 2530, and now we're at 3,000. All right, another way we can see this data is to use a trapezoidal approximation. So you've got to be good at remembering the area of a trapezoid. And then the other thing, let's switch to blue here, is that the trapezoids are kind of sideways. So I'm going to draw a curve here. And I'm going to have, let's do this. And I'm going to put in some partitions. And so where you need to see these trapezoids is that I'm going to kind of straighten off these edges. And so this thing, if I'm using my trapezoid area formula, kind of have to turn your head sideways. This is the height. This is one of the bases. And this is another base. Okay, so if I'm trying to find the area of this trapezoid, it's 1/2 the height times the sum of B1 plus B2. All right, so that's the way the trapezoid area formula works. If you notice, these trapezoids look a lot closer to approximating the area under the curve than a rectangle did, right? The rectangles, when we drew them, if I had a curve here, we were, chunking off quite a bit of the curve and not necessarily getting a very good approximation, right? We're missing some stuff at the top. The trapezoid is a little better approximation. All right, so let's do an example. This is another straight from an AP exam. It says, as a pot of tea cools, the temperature is modeled by a differentiable function h for 0 is less than or equal to t is less than or equal to 10, where t is in minutes and h of t is measured in degrees Celsius. Selected values of h of t are shown in the table. All right, and we're supposed to use a trapezoid approximation. All right, so let's look at what we have here. Use a trapezoidal sum with 4 subintervals to estimate. Now, this we've talked about briefly. Hopefully they mentioned in video 6.1. This part here is asking us to find, well, what is that area under the curve? That's what this represents, from 0 to 10. So I have some curve. The temperature, it looks like it's decreasing, right? Something's cooling off. So I have some function that's cooling off. And I want to know what's the area under the curve here from 0 to 10. Notice I'm not quite at 0. My graph's a little bit too steep. And we're going to divide some subintervals here. We're going to have 4 subintervals. So we'll just say this is our 10 here, okay? And we want to make a trapezoidal approximation. And then we're going to talk about what this maybe means at the end. All right, so as we have done in the past, we need to know the width of each one of these. So if we're going from 0 to 10 with 4 subintervals, the width of each one of these, which in this case is like thinking about the trapezoid formula again. So it's 1/2 the height times the sum of the 2 bases. All right. So if I think about my height here in this case is that width of the rectangle, so delta x. And again, it's going to be 10 minus 0. And we have 4 subintervals. So that's going to be 5/2. Right. So we're going to have, oh, but they're not even, oops, never mind. pay no attention to that. I should have looked at the table and the data in the table here. Normally we would do this if we didn't have a table. We would actually take the curve and divide it, but I forgot we're using a table. So we're going to have the height of this first trapezoid is 2. The height of our next trapezoid is 3 and 4. And our last one is 1. Okay. Notice back what my mistake here was, if our trapezoids had all been even, that's what we would do, right? But we don't have that this time. All right, so our first trapezoid, trapezoid 1, and we're going to have 4 of them, right? We have 4 subintervals. We're going to have 1/2 the height, and our height here is this first width, the first delta x, which is 2, times the sum of the 2 bases, and that's these 2 heights here, so 66 plus 60. Okay, that's trapezoid number 1. Trapezoid number 2, again, is 1/2. This time our height is 3, right? Our 3, remember h in this case is our delta x. When we think about our trapezoid formula, that's what that's talking about. So this time 1/2 the height times, on our bases this time, are 60 and 52. Our third trapezoid, we have 1/2. Its width is 4. The bases this time are 52 and 44. And our last trapezoid, we still have our 1/2. This time the width is 1. Our height is 1. And our 2 bases this time are 44 and 43. One thing that's kind of cool about the trapezoid formula, when we do have equal subintervals here, when our delta x's are all the same, if you notice, you always have this 1/2, 1/2, 1/2 thing. If these widths are all the same, delta x, delta x, delta x, you can take that all outside and makes an easier problem. And the other thing you notice, you have a 60 here and a 60 here, 52 and 52 and 44 and 44. So if the subintervals all have equal widths, there's some much easier ways to simplify it, but we don't have this time. All right, so if you remember, our problem was to not only find this, right? Remember, this is the area under the curve here. And then we're going to be doing this 1/10 thing. Well, let's think about what the area under the curve represents in this case. It talks about that this was a pot of tea that was cooling. And if you look at t equals 0, it was 66 degrees Celsius and so forth. And after 10 minutes here, it is cooled to 43 degrees. So this 1/10, right? If I figure I'm going from 0 to 10, or I do a 1 divided by 10, can you think of what that might represent? Right. So if I do this whole problem and I do my 1/10, I end up with a measurement of about 52.45 degrees Celsius. And what do you think that represents, especially when we do this 1/10? If you said it is the average temperature, you are correct. It is the average temperature in degrees Celsius of the, is it a pot? Of the pot from, oh, the pen's working well now. T equals 0 to T equals 10 minutes. Oh, that's a 10. Okay, so it's the average temperature. All right, let's talk about the behavior of these things, by the way. So this is kind of, you'll see this math notation for writing these. So right one, notice it's always got the delta x, that's the width. The right Riemann sum skips the first subinterval, so there's no 0. It starts at 1 and goes all the way to the very last one, which they're calling, it looks like I. If I look at the left, a left Riemann sum starts at x0, right? The 0 position. Oops, goes back, 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 keep adding. But a left Riemann sum does not include the very last one. It includes the one before. So that's the difference in these notations. The midpoint, notice we still have our delta x. but the value of the function is evaluated at the average of these x intervals, right? Or there's our 1/2 that we pull out, right? If we're doing a midpoint, add the two subintervals divided by 2, evaluate that into our function to get our height, right? We had this in a table and it was much easier. We didn't have to do this calculation by hand. Again, a trapezoid, you have 1/2 the height, and the height is that change in x. And then you have to evaluate the function at the first endpoint, the second endpoint, there's your sum of your two bases, add those together, add the next two, and so forth, right? If a function is strictly increasing, let me grab a pen here. If a function is strictly increasing, let's talk about what's happening here, right? So I'll draw some x and y axis here. Oh, that's beautiful. If I put in my rectangles, and I'm using right rectangles, so here's my first subinterval. If I draw my right rectangles, you can see when the function is increasing, these right rectangles are an overestimate of the actual sum. If I have an increasing function, my left rectangles, and again, I'll put some rectangles here, these left ones, right? Oops, that's really seriously under. The left rectangles are an underestimate. If my function is decreasing, okay, the opposite of that's going to be true. So here's a decreasing function. This time, I'll put in my subintervals. This time, my right rectangles are going to be an underestimate. And again, with a decreasing function, if I put in and I use my left rectangles, oops, my left rectangles this time are going to shoot over the curve and be an overestimate. All right, when we look at trapezoid approximation, it has to do with concavity. So a trapezoid is an underestimate if the graph is concave down. So let's draw a concave down curve. I kind of been doing that all along. So this is concave down. And my trapezoid approximation is an underestimate if it's concave down. So if you look, these trapezoids are going to fall below the curve. If the graph is concave up, I'll put some subintervals in here. This time when I draw my trapezoids, they're going to be above the curve, and it's kind of hard to see on mine. So they are going to be an overestimate. All right, so that's going to take us to our next problem. This is straight from an AP exam. It says the graph of the function f is shown above from 0 to 3. Of the following, which has the least value? All right, we haven't really talked about this first one, but this is exactly the area under the curve, right? If we had a way to calculate this exactly, that'd be it. So that's not going to have the least value. That's going to be pretty super close. So let's look at some things on here. We know it's decreasing. It's concave down. All right, so let's think about the things that we know already are going to be overestimates. So if it's concave down, we'll talk about that. So, well, let's do decreasing first. So decreasing, a left Riemann sum is going to be an overestimate. If it's concave down, a trapezoid approximation is going to be an overestimate. All right, so let's look at those two. Let's see if we see a left Riemann sum, 4 subintervals equal length, right Riemann sum, midpoint, so forth. All right, so we're going to rule out left because we already know that's going to be an overestimate. So it's not going to be the least. This is exactly it. So we're not going to look at that. Let's see, concave down, trapezoidal, concave down. We're going to rule that one out. So we're down to this. And we want the one with the least value. So remember, a right Riemann sum, if it's decreasing, is an underestimate. Midpoints tend to be more accurate. We kind of did some examples with Catherine. I think it was her trip from home to school or something. And the midpoint tends to be more accurate. This one is pretty far off the curve. So the answer we would choose is this. A right Riemann sum on a decreasing function is going to be an underestimate. All right, this time we have, oh, it's Catherine again. It says Catherine travels from her home to school. Let's find the distance Catherine travels, distance using a trapezoidal Riemann sum. All right, so we did this problem before, but we did not do a trapezoid for it. All right, so let's grab my pen here. Oops, go back. Oh, well, that was bad. Oh, PowerPoint, where'd you go? All right. Phew. That was fun. I did enjoy reading my mail. All right, hope there wasn't anything bad. So we have this continuous function and we want a trapezoidal Riemann sum. Okay, so we have 1/2. The height of the first one is 2 times 10 plus 14, right? Got to add those two bases or subintervals. Next one is 1/2. This time the height is 4. And we're going to do 14 plus 20. Our next width is 2, so we have 1/2 times 2. And the reason I'm doing 1/2 every time is, remember, that's the area of a trapezoid. All right, and this time we have 20 plus 15. Our next width is 7, so 1/2 times 7 times 15 plus 30. And then we have 1/2 times 5 times 30 plus 20. That's a half, by the way. And our final trapezoid is 1/2 times 5 again times 20 plus 10. All right. You might want to pause and check and make sure my math's all right, but I came up with, oh, it looks like it didn't complete it. I didn't find my final answer here. I'll leave that up to you guys. I was going to save you some work. But if you do that and then compare that to that answer we got before, because we did one like this, and I think we did, oh, we might have done a left Riemann sum for this. So compare it. Let's compare these two answers. And I didn't calculate it out. So I'll leave that up to you guys and we can check in class. All right, our very last problem finally says, grab my pen here. It says the temperature in water at a time t is modeled by a strictly increasing, super important, we know that. They're going to give you these little clues in the stem of the problem. Twice differentiable, okay, that's good to know. Remember, this is helping us realize that this function is continuous when they tell us it's differentiable. Super important. That means all of our nice calc theorems are going to apply. It says where WT is measured in degrees Fahrenheit and T is measured in minutes. At time T equals 0, the temperature of the water is 55 degrees. The water is heated for 30 minutes, beginning at time T equals 0. Values of WT at selected times for the first 20 minutes are shown in the table. For 0 is less than or equal to T is less than or equal to 20. The average temperature, remember, that's what this thing right here is, and this just is saying area under the curve. Use a left Riemann sub with the 4 subintervals indicated by the table to approximate this. Does this approximation overestimate or underestimate? All right, so one of the things we noticed, this was strictly increasing. So if we have an increasing function and we are using a left Riemann sum and a strictly increasing function, we already know this is going to be an underestimate, right? We haven't done any math, but we know it's increasing. We know we're using left Riemann sums here. So these rectangles are going to be an underestimate, right? So we've already been able to answer part of the problem without any math. All right, what we're doing in this problem is we have 120. We're using a left Riemann sum. We are using the 4 subintervals right here. So our first rectangle is 4 wide. We're using the left, so we're going to use 55. That's the left side of that rectangle. Our next width, we're going from 4 to 5 is, or 4 to 9 is 5. The left-hand width is 57.1. And again, remember, one thing to look for is if you're doing a left, you're going to leave off the last number. If you're using a right, you're going to leave off the first number. I think that's helpful to notice. Next one, we're going from 9 to 15, so that width is 6. And our left endpoint is 61.8. And our last one, we're going from 15 to 20. So we have 5 times 67.9. All right. So then we would multiply these. This looks like this is probably a calculator 1. We do all that work. We do all of it. We divide by 20. And again, I did not multiply this all out ahead of time, so I'll leave that to you guys. Use a left Riemann sum to approximate this. So this answer that we're going to get is the average temperature of the water. That's what we're trying to find. So the average temperature of the water is going to be whatever this answer is in degrees Fahrenheit. And we have already answered this part that says this is an underestimate. Okay, I hope this helped. You guys have a homework packet to do. What are our key takeaways? The area of under a curve can be approximated using a left to right midpoint or using a trapezoidal approximation. The area under the curve is represented by an integral, and that's that little wavy thing we've seen a few times here. It looks like this. That's an integral symbol. You'll have some function without kind of things, and you'll see this little dt, right? When they put numbers on the end, that's where we're getting a definite value here, right? When we looked at the curve, we might have like, we're looking at it from 1 to 3 or so forth, or we're doing an average from 0 to 10. You might have a 0 and a 10 and 1/10 out here. So that's the integral symbol. And that's all we have. So I'll stop the share here. And if you have any questions, you can email me. Go ahead and try to tackle that homework assignment I gave you. And there should be one more video for you to watch. Okay, good luck.